Hello, my friend. Welcome. If you found your way here, it's probably because you're curious about the universe and maybe also looking for some peace and rest. This video is designed for both. I'll guide you through the wonders of Einstein's special relativity in a voice and pace meant to help you drift into sleep. Whether you stay awake to learn or slowly close your eyes as the words carry you, you'll know you're in the right place. Chapter 1. What is special relativity? A quiet introduction. In the quiet world of physics before the 20th century, the universe seemed stable and predictable. The framework laid down by Isaac Newton in the 17th century described the motions of planets, falling apples, and cannonballs alike with extraordinary precision. For more than 2 centuries, this classical worldview offered comfort and clarity. Space was thought to be an unchanging stage upon which the drama of matter unfolded, and time was the universal rhythm to which everything danced. Every observer, it seemed, could agree on the ticking of the cosmic clock, and the distances in the vast theater of the universe appeared absolute. But as the 19th century unfolded, small cracks began to appear in the seemingly perfect structure. These cracks did not come from any failure of Newton's equations in describing everyday life, but from deeper questions raised by the strange behavior of light and electricity. James Clerk Maxwell had unified electricity and magnetism into a single, elegant theory, one that predicted electromagnetic waves moving through space at a fixed speed. This speed matched the measured speed of light, leading to the remarkable conclusion that light itself was a form of electromagnetic radiation. But this brought with it a puzzle. If light was a wave, what medium did it move through? Ocean waves need water, sound waves need air. And so physicists of the time imagined a kind of invisible medium called the luminiferous ether, filling all of space. The ether was supposed to be the substance against which absolute motion could be measured, the universal backdrop for the vibrations of light. Yet, as experiments tried to reveal this medium, it remained elusive. The most famous of these was the Michelson-Morley experiment of 1887, which attempted to measure the Earth's motion through the ether by detecting tiny differences in the speed of light moving in different directions. The result was baffling. No matter how carefully they looked, no difference was found. Light appeared to move at the same speed in every direction, regardless of the motion of the Earth. This result was not just puzzling, it was revolutionary. If the ether did not exist, then what did it mean for light to have a constant speed? If light traveled at the same speed no matter how fast an observer moved, then the basic assumptions about space and time had to be reconsidered. Yet for nearly 2 decades, no one fully resolved the dilemma. Some proposed that the apparatus of Michelson and Morley had contracted as it moved through the ether, a desperate explanation that patched the problem but offered no real clarity. Physics stood at a threshold, sensing a transformation but unable to step through. Into this uncertainty stepped a young man working as a patent clerk in Bern, Switzerland. Albert Einstein was not a professor, nor part of the great European universities. But he carried with him an instinct for clarity, an ability to see through the clutter of assumptions and imagine a world built on simple, universal principles. In 1905, in a paper modestly titled On the Electrodynamics of Moving Bodies, he proposed a daring idea. Perhaps there was no ether, no hidden medium. Perhaps space and time themselves were not absolute at all. Einstein began from 2 postulates. The first was the principle of relativity. The laws of physics are the same in all inertial frames of reference, meaning that whether you are standing still or gliding at constant speed, the fundamental rules of the universe do not change. This was already familiar from Galileo's work centuries earlier, who had noted that the motions inside a smoothly sailing ship could not reveal whether the ship was moving steadily or at rest. The second postulate, however, was far more radical. The speed of light in a vacuum is constant, independent of the motion of the source or the observer. No matter how fast you chase after a beam of light, it will still recede from you at the same speed. At first glance, these two statements seem almost trivial, yet taken together they demand a complete reshaping of our understanding. For if the speed of light is always the same, then something else must give way. That something is our intuitive sense of time and space. Time cannot tick at the same rate for everyone if light is to maintain its constancy. Space cannot remain rigid if measurements of distance are to stay consistent across different observers. The absolutes of Newton's universe give way to a flexible fabric where intervals of time and space depend on motion and perspective. To appreciate the magnitude of this shift, imagine two observers watching the same event. One stands on a train platform, the other rides a train rushing past. In the Newtonian world, both would agree on when the event happened and where. But Einstein's insight revealed that they may disagree on both, not because one is mistaken, but because reality itself is relative to their state of motion. Their measurements of time and distance would differ, yet each would be entirely correct within their own frame of reference. There is no single universal clock, no shared grid of absolute space. Instead, the universe offers a deeper consistency. The laws of physics and the speed of light remain unbroken, even as time and space bend around them. This new picture did not emerge without resistance. To discard centuries of assumption required a boldness that unsettled many. Yet the elegance of Einstein's reasoning could not be denied. He showed that time slows down for moving clocks, distances contract for moving rulers, and events that seem simultaneous to one observer may not be simultaneous to another. These were not philosophical speculations, but logical necessities flowing from the postulates. The mathematics that supported them, though simple compared to the machinery of later physics, left no room for doubt. What makes special relativity so extraordinary is that it does not rely on exotic conditions or distant galaxies. It applies to every object moving at any speed. In daily life, the effects are too small to notice because we move so slowly compared to light. But at speeds approaching the cosmic limit, the consequences become dramatic. A spacecraft traveling near the speed of light would find its onboard clock ticking more slowly compared to clocks on Earth. Its length in the direction of motion would contract when measured by outside observers. The passengers would experience their journey as perfectly normal, yet the outside world would record a very different passage of time and distance. The term special in special relativity refers not to its importance, but to its scope. It is special because it applies only to inertial frames, those moving at constant speeds without acceleration. Gravity and acceleration require the broader framework of general relativity, which Einstein developed a decade later. But even within its limited domain, special relativity reshaped physics so profoundly that it became the foundation for all that followed. It revealed a universe woven together by space and time into a single continuum, a fabric whose structure could stretch and shift depending on motion. The implications extended beyond physics into philosophy and culture. The idea that time is relative, that simultaneity is not universal, challenged deep intuitions about reality. It forced people to reconsider what it means for events to happen and whether there is an objective now. Philosophers debated whether relativity undermined free will or supported determinism, while artists and writers found inspiration in the fluidity of time and space. The 20th century was already an era of upheaval, and Einstein's work mirrored the shifting sands of human thought. And yet, for all its revolutionary character, special relativity retains a serene simplicity. At its core are just two postulates, each easy to state and grasp, yet together, leading to consequences that still astonish us. It shows that the universe is not built on rigid absolutes, but on relationships, that reality is shaped by perspective without ever descending into chaos. Light, the fastest thing in existence, becomes the anchor around which space and time arrange themselves. It is worth pausing here to reflect on the humility of its origins. Einstein wrote his paper while working at the patent office, reviewing the inventions of others while nurturing his own ideas in spare hours. He had no laboratory, no team of assistants, no powerful observatory. What he had was the ability to think deeply, to imagine riding alongside a beam of light and asking what the universe would look like from that impossible vantage point. From such thought experiments came insights that reshaped physics forever. Special relativity is, in a sense, a reminder of how fragile our intuitions can be. We assume that time is universal because our lives unfold at human speeds where differences are imperceptible. We assume that distances are fixed because we have never ridden a spacecraft near light speed. But the universe is not beholden to human scale. The cosmos is vast, the speed of light immense, and reality accommodates conditions far beyond everyday experience. In that broader view, our familiar absolutes dissolve, replaced by a deeper harmony. When you look up at the night sky, the light reaching your eyes may have traveled for hundreds or thousands of years. In that journey, it has passed through a universe where time stretches and distances contract depending on perspective. Each photon carries not just information about its source, but a testament to the relativity of space and time. The stars above us are not fixed points on a rigid canvas, but actors in a universe where the stage itself bends and shifts. And as you drift towards sleep, it may be comforting or perhaps unsettling to realize that even something as fundamental as time is not absolute. The seconds ticking on your bedside clock belong to your frame of reference, but to a distant traveler, they may stretch or shrink. In this way, special relativity invites us to see reality not as a single fixed truth, but as a network of perspectives, each valid, each woven together by the unchanging speed of light. Perhaps in that realization lies a quiet lesson beyond physics, that the universe is not designed to match our intuition, but to reveal its own deeper order if we dare to look closely. Chapter 2. The Principle of Relativity, Physics for Everyone, Everywhere. When Einstein published his paper in 1905, one of his most disarmingly simple statements was that the laws of physics are the same for all observers moving at constant velocity relative to one another. To the untrained ear, this might not sound revolutionary at all. After all, Galileo had said something similar centuries before, that the motions of objects inside a smoothly sailing ship cannot reveal whether the ship is at rest or moving steadily forward. If you drop a ball, it falls to your feet whether the ship is anchored or gliding across a calm sea. You cannot tell by such an experiment if the ship is moving. This was the original idea of relativity, and Einstein openly acknowledged that his own principle of relativity grew directly out of that tradition. But in the 19th century, physicists were beginning to wonder if there might be hidden subtleties, particularly when it came to the behavior of light and electromagnetism. Galileo's statement applied to mechanics, the physics of motion and forces, but Maxwell's new laws of electromagnetism added complexity to the picture. His equations seemed to describe waves rippling through space, and waves, as far as physicists understood them, required a medium. That medium was imagined as the ether, and if the ether existed, then it could define a kind of absolute rest. You could, at least in principle, measure your velocity relative to it. The Michelson-Morley experiment challenged that notion, showing that no matter how carefully you measured the speed of light in different directions, you would always get the same value. Einstein's bold move was to declare that Galileo's principle of relativity is not limited to mechanics, but extends to all of physics, including electromagnetism. That means there is no absolute rest, no hidden ether, no preferred frame of reference. If you are drifting in a spaceship with the engines off, you can perform any experiment you like, mechanical or electromagnetic, and you will never be able to prove whether you are at rest or in uniform motion. The universe does not privilege one state over the other. This is what physicists mean when they talk about inertial frames. An inertial frame is simply a state of motion that does not involve acceleration. Imagine sitting in a train moving smoothly on straight tracks. If the ride is steady enough, you might not even know you are moving. Inside the cabin, you can toss a ball to a friend, let water drip from a bottle, or swing a pendulum, and everything behaves exactly as it would if the train were parked. You would only notice the difference if the train accelerated, braked, or turned. The moment acceleration enters the picture, the principle of relativity no longer applies in its simple form. But as long as you move steadily, you and an observer on the platform can both apply the laws of physics, and each will find them to hold without contradiction. Einstein elevated this idea from a mechanical curiosity to a universal truth. This is why the theory is called special relativity. The special refers not to its importance, but to its restriction to inertial frames. It says that in every inertial frame, the laws of physics take the same form. This is not merely a philosophical claim. It has deep mathematical implications. If you write down Maxwell's equations for electricity and magnetism, or Newton's second law of motion, they must look the same to all inertial observers. No one is given a special version of the laws just because they happen to be moving. This principle, however, leads us to rethink how we understand motion itself. Imagine again the train example. If you are inside the train and you drop a ball, you will say the ball falls straight down. But an observer on the platform will say the ball follows a diagonal path, moving forward with the train while falling downward. Both descriptions are correct, each relative to its own frame of reference. The difference is reconciled because the observers disagree about the decomposition of the ball's motion into vertical and horizontal components, not because the ball behaves differently. The principle of relativity ensures that both observers will use the same underlying laws to explain what they see. Now, when we extend this principle to include light, the picture becomes more subtle. Suppose the train has a lamp mounted on the ceiling, and it shines a beam of light straight downward. For the passenger inside, the light moves vertically, hitting the floor directly below the lamp. But for the observer on the platform, the light follows a diagonal path, since the train is moving forward while the beam travels downward. If both observers measure the speed of that light, however, they will both find the same value. This invariance of light's speed is consistent with the principle of relativity, but it forces us to let go of the idea that time and distance are absolute. What makes the principle of relativity so profound is that it acts as a safeguard for the coherence of physics. Without it, we might expect nature to play favorites, with different sets of rules applying depending on how fast or in what direction you move. That would make physics a patchwork, fractured and inconsistent. Instead, Einstein's principle provides a kind of universal equity. It declares that the cosmos does not distinguish between travelers gliding smoothly at different speeds. Every inertial observer is equally entitled to describe the world with the same physical laws. One might ask, why should this be true? Why shouldn't the universe have a special reference frame, a cosmic anchor against which all motion is measured? After all, in everyday life, we constantly compare our speeds to the ground beneath our feet. If I tell you I'm driving at 100 kilometers per hour, it is understood that I mean relative to the road. But physics insists that no such absolute stage exists. The Earth itself is spinning on its axis and orbiting the Sun. The Sun is circling the center of the Milky Way, which in turn drifts relative to other galaxies. At no point can we say we are truly at rest. Motion only has meaning as a relation between objects. Einstein's insight removed the need for an invisible medium like the ether because it was redundant. The laws of physics do not care about your velocity relative to an imagined backdrop. They only care about relative velocities between actual objects. If one spaceship flies past another at a constant speed, each crew sees the other in motion, and each is entitled to call themselves at rest. There is no experiment either ship can perform to prove otherwise. This radical symmetry lies at the heart of the principle of relativity. Over the years, experiments have confirmed this principle again and again. Particle accelerators routinely propel electrons and protons to speeds close to that of light. The laws governing their behavior, how they bend in magnetic fields, how they scatter off one another, are identical to the laws describing particles moving more slowly. There is no hidden correction that appears only at high speeds. Astronomical observations confirm the same principle. Whether light comes from a nearby laser or a distant quasar, its speed is constant, indifferent to the motion of its source. What is striking about the principle of relativity is its universality. It does not apply only to esoteric laboratories or rare cosmic events. It applies everywhere, to every inertial observer. This makes it one of the most democratic principles in science. No matter where you are in the universe, no matter how fast you are moving, as long as your speed is steady, you are entitled to claim your perspective as valid. There is no privileged vantage point. This universality also reshapes how we think about the very structure of space and time. If the laws of physics must look the same for all observers, then the transformations between different frames of reference must have a certain symmetry. These transformations are not mere translations or rotations, as in classical mechanics, but Lorentz transformations, which weave time and space together in order to preserve the constancy of light's speed. This is where special relativity acquires its distinctive flavor. The principle of relativity alone does not dictate the details, but once combined with the invariance of light's speed, it forces us into a new geometry of space-time. One might say that the principle of relativity is the philosophical heart of Einstein's work, while the invariance of light is the physical anchor. Together, they form a foundation upon which the strange but consistent edifice of relativity is built. Neither alone would be sufficient to overturn Newton's absolutes, but together they demand a reality where clocks tick differently depending on motion, rulers shorten when measured in flight, and simultaneity dissolves as an illusion of perspective. For students encountering relativity for the first time, this principle can feel abstract. It can seem like a statement about fairness rather than physics. Yet its power lies in its ability to guide our understanding across domains. Consider, for instance, the design of GPS satellites. They orbit the Earth at high speeds and experience time differently than clocks on the ground. The system must account for both special and general relativistic effects to provide accurate navigation. If the principle of relativity did not hold, if different inertial frames required different physical laws, such corrections would be incoherent. But because the principle ensures consistency, we can calculate and adjust with confidence, and the system works. The principle of relativity is, in essence, an assertion of unity. It ties together the experiences of all observers, insisting that beneath the shifting appearances lies a set of rules that never changes. This unity is not obvious to our senses, which are attuned to human scales and speeds. But the deeper we peer into nature, the more clearly we see its imprint. The universe does not indulge our intuition of absolutes. Instead, it offers a harmony of relative perspectives, bound together by unchanging laws. And as with many truths in science, this principle carries a quiet existential resonance. It tells us that there's no central stage in the universe, no throne from which to declare a privileged view. Every perspective is valid, provided it moves steadily, and every observer carries with them the same laws of nature. In this way, relativity reflects not just physics, but a certain humility. We are not at the center. We are not special in our vantage point. We are part of a grand network of observers, all moving, all measuring, all connected by the same silent rules of existence. Perhaps there is comfort in this. As you drift toward sleep, imagine the universe filled with countless observers on ships, planets, or drifting stations, each one watching, each one describing reality in their own frame. None of them is wrong. None of them is more privileged than another. The cosmos does not play favorites. It embraces all perspectives equally, and in doing so, it reveals a truth both scientific and human, that reality is not anchored to a single view, but to the shared consistency that binds them all together. Chapter 3: The Speed of Light, a Universal Limit. The discovery that the speed of light is not just a number, but a universal constant is one of the great turning points in human understanding of nature. In ordinary experience, speed feels like something relative, something that depends on the observer. If you are walking through a park and a cyclist overtakes you, you describe the bicycle as moving quickly relative to you. Someone else standing on the sidewalk may measure a different speed, depending on their perspective. In Newton's world, this was a natural and unquestioned feature of motion. Velocity simply added and subtracted depending on the frame of reference. If you throw a ball forward on a moving train, its speed relative to the ground is the sum of the train's speed and the throw. The arithmetic of motion felt intuitive, and for centuries it matched the observations of human-scale life. But light refused to obey these simple rules. As physicists investigated the nature of electromagnetic waves in the 19th century, a curious fact emerged. Light seemed to move at the same speed, no matter how you approached the problem. Maxwell's equations predicted this speed with beautiful precision. giving a value that today we know to be about 299,792 kilometers per second in a vacuum. Unlike the motion of sound or water waves, this speed appeared to be fixed, unyielding, and immune to the ordinary arithmetic of relative motion. The Michelson-Morley experiment made this fact plain by showing that no motion of the Earth through space could alter the measured speed of light. The strangeness of this result cannot be overstated. Imagine again the moving train. If you run toward the front of the train and shine a flashlight ahead of you, common sense suggests that the light beam should move faster relative to the ground than if you had shone it while standing still. In Newtonian mechanics, the speeds would simply add. But in reality, the beam travels at exactly the same speed in both cases. The universe refuses to allow the speed of light to be altered by the motion of the source. This is not just a technical detail. It is a fundamental truth about the structure of reality. Einstein recognized that if the speed of light is constant, then our understanding of time and space must bend to accommodate it. Instead of light's velocity shifting with the motion of its source, time itself must stretch and distances contract to ensure that all observers measure the same speed. This adjustment is so counterintuitive that it requires a complete reframing of what we mean by space, time, and simultaneity. To appreciate why this is so radical, it is helpful to compare light to sound. If you are standing still on the ground and an ambulance approaches with its siren on, you hear the pitch rise because the sound waves are compressed. If you move toward the ambulance, the pitch rises further because your motion adds to the relative speed of the waves. Sound depends on the air as a medium, and velocities of source and observer both matter. Light, however, has no such dependence. Whether you move toward or away from its source, its speed remains fixed. You may still observe a change in frequency, known as the Doppler effect, but the velocity itself is untouchable. This constancy has profound consequences. It means that no matter how hard we try, no object with mass can ever be accelerated to the speed of light. As an object's speed increases, its kinetic energy grows not linearly, but in a way that makes further acceleration increasingly difficult. Approaching light speed, the required energy becomes effectively infinite. The speed of light therefore stands as a cosmic speed limit, not only for particles and spacecraft, but also for the transmission of information and cause and effect relationships. Nothing can outrun light without violating the fabric of relativity. The universality of this limit is not a matter of conjecture, but of experimental certainty. High-energy particle accelerators, like those at CERN, propel protons to velocities within a fraction of a % of light speed. Yet no matter how much energy is poured into them, the protons never quite reach the limit. Their masses increase, their lifetimes extend, their behavior matches exactly what relativity predicts, but the speed itself remains inviolate. The universe enforces this law with unwavering consistency. Even more striking is the role of the speed of light beyond the domain of optics. In modern physics, it is not just the speed of light, but the maximum speed at which any interaction can propagate. Gravitational waves, ripples in space-time itself, move at this same speed. Information about the position or state of a particle cannot travel faster. This makes the speed of light the ultimate governor of causality. If a star explodes in a distant galaxy, its light cannot reach us before the time set by this limit. Until then, for all practical purposes, the event does not yet exist for us. The cosmic speed limit is the universe's way of ensuring order in the sequence of cause and effect. This principle reshapes even how we think about distance. Astronomers routinely measure the universe in light years, the distance light travels in a year. This unit is not chosen out of convenience, but necessity. Because information cannot travel faster than light, distance and time are bound together. To look out into the cosmos is to look back into time. When we see a galaxy a billion light years away, we are seeing it as it was a billion years ago. The light's finite speed transforms the night sky into a time machine, one that reveals not just where, but when the light began its journey. The constancy of light speed also underlies technologies that permeate daily life. Global positioning system satellites must account for both special and general relativistic effects in order to maintain accuracy. The clocks on board experience time differently due to their velocity and their position in Earth's gravitational field. Without correcting for relativity, GPS would quickly accumulate errors that render it useless. The fact that your phone can tell you where you stand within a few meters is a practical triumph of the cosmic speed limit. Still, the most profound implication of the speed of light as a universal limit is philosophical. It forces us to abandon the dream of instantaneous communication across space. No signal, no matter how advanced our technology becomes, can leap across the galaxy faster than light. This creates a fundamental isolation between stars, between civilizations, even between the farthest reaches of our own observable universe. If intelligent beings exist in a galaxy millions of light years away, they may have already sent signals toward us, but we will not know until that light arrives, long after both civilizations may have changed or vanished. The speed of light sets not only a physical, but a communicative boundary on existence. There have been attempts to imagine what it would mean to surpass this limit. Science fiction often plays with ideas of warp drives, wormholes, or tachyons. Hypothetical particles always move faster than light. Yet within the framework of relativity, such ideas come with paradoxes that unravel the very order of causality. If signals could move faster than light, it would be possible to send information backward in time, creating contradictions where an effect could precede its cause. The prohibition on faster-than-light travel is not merely a rule of mechanics, but a safeguard against logical collapse. At the same time, quantum physics has introduced subtleties that complicate this picture without breaking it. Phenomena like quantum entanglement seem to allow instantaneous correlations between particles separated by vast distances. Yet these correlations cannot be used to transmit information faster than light. The cosmic speed limit holds firm, even as the quantum world offers strange hints that reality is more interconnected than our macroscopic intuition allows. One might ask why light, of all things, should play this defining role. The answer lies in the structure of Maxwell's equations, which describe electromagnetic waves. They predict that these waves travel at a speed determined by the electric and magnetic properties of the vacuum itself. There is no need for a medium like air or water. The vacuum is sufficient. The number that emerges from these equations matches the observed speed of light, tying the behavior of a fundamental constant to the very fabric of empty space. Einstein's genius was to take this number not as an accident, but as a cornerstone of physics. This reimagining of light as the universe's limiting speed reveals a profound unity in nature. It shows that what we perceive as illumination from a lamp or the glow of a star is not just a convenient physical phenomenon, but a manifestation of the deepest laws of space-time. Light's speed is not an incidental property of photons. It is a reflection of the structure of reality itself. In considering this, one cannot help but feel a sense of awe. The limit imposed by light is not something that can be overcome by engineering or ingenuity. It is woven into the nature of existence. It binds together time, space, and causality, ensuring that the universe remains coherent. And yet, far from limiting us, it has opened pathways to deeper understanding. By respecting this limit, physics has unlocked technologies that guide spacecraft across the solar system, allow us to peer into the earliest moments of the cosmos, and connect billions of people through global networks. As you think about this universal constant, it may be worth reflecting on what it says about our place in the cosmos. The speed of light tells us that we are bound by a horizon, that our knowledge of the universe can only extend as far as light has had time to travel. Beyond that, there are mysteries forever beyond our reach. The light that surrounds us is a messenger, but it is also a gatekeeper, deciding how much of reality we can ever know. In that recognition lies both humility and wonder. Perhaps, as you drift towards sleep, you can imagine yourself floating in the silence of space, watching beams of light race outward in every direction. They move at the ultimate speed, faster than anything you could ever hope to follow, carrying with them the story of stars, galaxies, and time itself. And maybe in that thought, you find a quiet sense of belonging, not as one who can outrun the universe, but as one who bears witness to its endless unfolding, carried always at the pace of light. Chapter 4. Time Dilation. Why Moving Clocks Tick Slower. Few consequences of Einstein's special relativity are as startling and counterintuitive as time dilation. At first glance, the idea that time itself flows differently for observers in relative motion seems impossible, almost paradoxical. Time is something we take for granted as universal. A second on one person's watch should be the same as a second on anyone else's. This was the comfortable assumption of centuries of physics and everyday life. Yet relativity tells us that this is not the case. Time is not absolute but depends on motion, and the faster you move relative to another observer, the slower your own time passes compared to theirs. This is not science fiction or philosophical speculation. It is a rigorously tested and experimentally confirmed fact. From the operation of satellites orbiting Earth to the behavior of subatomic particles racing through accelerators, time dilation has become one of the most well-established truths of modern physics. To understand it, we must follow the path Einstein took in realizing that the constancy of the speed of light demands a new picture of time itself. Consider a thought experiment often used to introduce the concept. Imagine a spaceship moving smoothly through space at a constant velocity. Inside the ship is a clock unlike any familiar timepiece. Instead of gears or digital displays, this clock is built from light. A beam of light bounces between two mirrors, one on the floor and one on the ceiling, and each round trip of the beam marks a tick of the clock. To an observer inside the ship, the light simply travels up and down between the mirrors, and the clock ticks steadily. Now imagine another observer outside the ship, watching it pass by at great speed. To this observer, the light beam does not travel straight up and down. Because the ship is moving, the light traces out a diagonal path, like the bouncing of a ball inside a moving train. The beam has to cover more distance between the mirrors from this outside perspective. Yet the speed of light is the same for both observers, and since the outside observer sees the light traveling a longer path at the same speed, the intervals between ticks must be longer. In other words, the clock inside the moving ship runs slower when observed from the outside. This simple thought experiment reveals the essence of time dilation. Motion alters the measurement of time. For the passenger inside the ship, nothing feels unusual. The clock ticks normally and life proceeds as expected. But to the outside observer, everything inside the ship appears to move more slowly. The heartbeats of the passengers, their conversations, even their aging, all unfold at a reduced pace relative to the outside world. The striking feature of time dilation is that it is not just an illusion or a trick of perspective. Both observers are correct in their own frames of reference. Each has their own proper time, measured by clocks at rest in their frame. Relativity tells us that there is no single universal time flowing everywhere at once. Instead, time is bound to motion and must be described relative to the observer. At everyday speeds, this effect is imperceptible. If you walk down the street or ride in a car, the difference in time flow compared to a stationary observer is vanishingly small, far beyond the resolution of any clock you carry. But at speeds approaching the speed of light, the effect becomes dramatic. A spacecraft moving at 99% the speed of light would experience time at less than half the rate of a stationary observer. Push closer to the limit, and the dilation grows even more extreme. In the ultimate case of moving exactly at the speed of light, something only massless particles like photons can do, time does not flow at all from the particle's perspective. For a photon, there is no before or after. Its journey from emission to absorption is timeless. The experimental confirmation of time dilation came swiftly after Einstein's predictions. In the mid-20th century, physicists studied particles known as muons, created when cosmic rays strike Earth's atmosphere. Muons are unstable and decay with a well-known lifetime. If they traveled at ordinary speeds, few would survive the trip to Earth's surface. Yet detectors found far more muons than expected. The explanation was time dilation. From the muons' perspective, only a short time had passed as they sped toward the ground at near light speeds. Their internal clocks ran slower relative to Earth's frame, allowing them to live long enough to reach detectors. This was one of the earliest and most dramatic confirmations of relativity's predictions. Further experiments have pushed the verification of time dilation to extraordinary precision. Atomic clocks flown on airplanes or mounted on satellites show measurable differences compared to clocks on Earth. The famous Halfili-Keating experiment of 1971 flew atomic clocks around the world on commercial airliners and compared them to clocks left at the U.S. Naval Observatory. The traveling clocks returned with times shifted by amounts exactly predicted by relativity, accounting for both their speeds and their altitudes in Earth's gravitational field. Modern GPS systems must include these relativistic corrections, or they would drift by kilometers each day. Without accounting for time dilation, the entire infrastructure of global navigation would fail. The reality of time dilation also introduces fascinating thought experiments. The most famous is the so-called twin paradox. Imagine identical twins, one of whom remains on Earth while the other travels on a spacecraft near the speed of light. Upon returning, the traveling twin will have aged less than the one who stayed home. The paradox arises because from the traveler's perspective, it seems the Earth was moving, and so one might expect the earthbound twin to be younger. The resolution lies in the fact that the traveling twin must accelerate and decelerate to make the round trip, breaking the symmetry of the situation. Relativity predicts unambiguously that the traveler will indeed be younger, and this has been supported by experiments with fast-moving particles. Time dilation challenges our most basic intuitions. We are used to thinking of time as a river, flowing at the same rate for all. Relativity reveals it as more like a network of streams, each flowing at its own rate depending on the motion of the observer. Yet this does not lead to chaos. The laws of physics ensure consistency between frames, and the discrepancies can always be calculated precisely. Time dilation is not a breakdown of order but a reshaping of it, woven into the geometry of space-time. There are subtle consequences for our understanding of causality. Because time flows differently in different frames, the ordering of events can depend on motion. Two flashes of lightning that appear simultaneous to one observer may occur at different times for another. But relativity preserves the sequence of cause and effect. If one event can influence another, all observers agree on their order. The slowing of clocks does not undermine causality, but ensures that it remains consistent across all perspectives. This understanding also leads us into the realm of astrophysics and cosmology. Time dilation plays a crucial role in the life cycles of stars and the dynamics of black holes. As matter spirals into a black hole, distant observers see its processes slow down, appearing to freeze near the event horizon. From the falling matter's own perspective, however, time flows normally. The difference is an extreme form of time dilation caused not just by motion but by gravity, a domain belonging to general relativity, but built upon the same principle that time is not absolute. Even at the scale of the expanding universe, the redshift of light from distant galaxies is partly understood in terms of the stretching of time and space. The human implications are equally striking. If interstellar travel were ever achieved at relativistic speeds, crews could journey for what seemed like only a few years to them, while decades or centuries passed on Earth. For the travelers, the voyage would be brief, but for those they left behind, entire generations could come and go. Time dilation means that explorers of the cosmos would always be out of step with the worlds they departed, returning as strangers to futures they never lived. And yet, despite the unsettling implications, there's also a quiet beauty in the idea. Time dilation reminds us that the universe does not conform to human expectations. It operates according to deeper rules, rules that remain consistent across all scales and situations. The fact that our technology must correct for relativity every time you open a map application on your phone is a reminder that this strange truth is not abstract. It is woven into the everyday world, even if we do not notice it directly. Perhaps the most humbling realization is that time itself, the very medium of our existence, is not fixed. It bends and flexes with motion, and its flow is not universal but relative. For all our efforts to measure it, divide it into hours, and regulate it with atomic precision, time is not a simple backdrop. It is dynamic, intertwined with space and motion, part of a larger continuum that cares nothing for our intuitions. And maybe there is something existential to be learned here. If time flows differently depending on where you are and how you move, then perhaps our own sense of permanence is also more relative than we imagine. We measure our lives by clocks and calendars, but those are only one perspective among many. The universe holds countless timelines, all valid, all unfolding in their own rhythm. As you rest, you might consider that somewhere out there, aboard a spacecraft racing near the speed of light, time itself is passing differently, yet just as truly. The cosmos, vast and indifferent, carries every clock at its own pace, reminding us that even the seconds we hold most dear are part of a greater relative fabric of reality. Chapter 5. Length Contraction. Space shrinks when you move. Among the many strange predictions of special relativity, length contraction often feels the most visual, the one easiest to picture and at the same time the hardest to truly believe. Time dilation suggests that moving clocks tick more slowly, which challenges our intuitions about time, but remains abstract until we imagine real experiments with particles or spacecraft. Length contraction, however, tells us that objects themselves, physical rulers, spaceships, planets, literally change their lengths depending on their state of motion. The universe insists that when an object moves relative to you, it becomes shorter in the direction of its motion. This shrinking of space is not an illusion or a trick of perception. It is a real, measurable effect arising directly from the same principles that demand time dilation. If the speed of light is constant for all observers, then space, as well as time, must bend in response. The contraction of lengths is the counterpart of the dilation of time, each balancing the other to preserve the invariance of light's speed and the consistency of physical laws. To see why, consider once more the idea of measuring distance with light. Imagine that you want to determine the length of a spaceship as it speeds past at a significant fraction of the speed of light. You set up detectors to record the times when the front and back of the ship pass by. From your perspective, the ship is moving, and the time interval between the passing of the two ends allows you to calculate its length. Yet when you compare this length to what the crew inside the ship would measure with their own rulers at rest, you find a discrepancy. To you, the ship is shorter than it is for them. The faster it moves, the more its length contracts along the direction of travel. The key to understanding this lies in the relativity of simultaneity. To measure the length of a moving object, you must note the positions of its front and back at the same time in your frame of reference. But simultaneity is not absolute. What counts as the same time for you may not be simultaneous for the crew inside. When each frame insists on applying its own notion of simultaneity, the result is a difference in measured length. Neither measurement is more real than the other. Each belongs to the perspective of the observer making it. Importantly, length contraction does not mean that people or objects are squeezed in their own experience. The crew inside the spaceship notices nothing unusual. Their rulers remain the same, their bodies unchanged, their environment perfectly normal. It is only from the outside, relative to observers who see the ship moving, that the contraction appears. This reciprocity is central to relativity. Each observer sees the other as subject to these effects, while feeling none of them in their own frame. Reality allows for both views, and no absolute perspective adjudicates between them. The effect becomes more dramatic as speeds approach that of light. At half the speed of light, the contraction is modest, barely noticeable with ordinary tools. But at 90%, the length shrinks to less than half of its rest value. At 99%, it becomes a fraction of its original size. Push even closer to light speed, and the contraction becomes extreme. In the theoretical limit of moving at light speed, something that massive objects cannot achieve, the length along the direction of travel would contract to zero. Though unreachable in practice, this illustrates the principle that motion reshapes not only time, but also space itself. Experiments confirm length contraction indirectly through the same processes that confirm time dilation. Particles accelerated to near light speeds in laboratories live longer than expected and travel farther than they otherwise could, a result that only makes sense if distances in their frame are shorter than in ours. Muons created in the upper atmosphere, for example, reach Earth's surface in far greater numbers than Newtonian physics would allow. From our frame, this is explained by their slowed decay. From the muon's own perspective, however, the atmosphere itself is contracted, compressed along the line of their motion, allowing them to traverse it in their short lifetimes. Both descriptions are correct, each belonging to its own frame. The implications of length contraction ripple outward into our understanding of the universe. It forces us to abandon the comforting notion of fixed dimensions. Objects do not possess one true length independent of context. Instead, length is relative, tied to the observer's state of motion. This relativity does not create inconsistency but enforces a deeper consistency, ensuring that all observers, regardless of their speed, agree on the fundamental laws of physics. Length contraction also plays a role in the resolution of paradoxes. One classic example is the so-called ladder paradox, in which a ladder moving at relativistic speed is said to fit entirely inside a barn shorter than the ladder's rest length. From the barn's frame, the ladder contracts and fits. From the ladder's frame, the barn contracts and cannot contain it. The paradox dissolves when one accounts for relativity of simultaneity. For the barn observer, the entire ladder is inside at one instant. For the ladder observer, the front is leaving before the back has entered. Both perspectives are correct within their own frames, and no contradiction exists. In practical terms, length contraction is less directly observed than time dilation, but its consequences are no less real. The design of particle accelerators, the interpretation of cosmic ray showers, and the analysis of high-energy astrophysical phenomena all rely on its predictions. Without accounting for contraction, the observed paths and interactions of particles would be inexplicable. The principle also extends beyond physical rulers to the very structure of space-time. Just as time intervals stretch depending on motion, spatial intervals compress. Together, these effects maintain the invariant speed of light, binding time and space into a single fabric. This unity is why physicists speak not of separate entities, but of space-time, where events have coordinates in both space and time, and transformations between frames weave the two together. For those encountering the idea for the first time, it can feel like a violation of common sense. How can the same object have different lengths depending on who measures it? Yet the lesson of relativity is that length is not an intrinsic property, like mass or charge, but a relational one. To ask for the length of something without specifying the frame of reference is meaningless. Length, like time, only exists in context. Astrophysics provides striking illustrations of this principle. Jets of particles streaming from active galactic nuclei, for example, travel at speeds close to that of light. Observations of their apparent brightness and structure must account for relativistic contraction and time dilation to make sense. Without these corrections, the distances and timescales would not align with the physics of emission and propagation. The very appearance of the cosmos in high-energy phenomena is shaped by relativity. Even within the realm of speculative exploration, length contraction carries weight. If humans were ever to travel at relativistic speeds, entire interstellar distances would contract in their frame. A journey to a star 20 light-years away, which would take decades in Earth's reckoning, could feel dramatically shorter to the crew aboard. The universe, in effect, becomes smaller for those who move quickly through it. While no technology we possess today can approach such speeds, the principle illustrates how relativity reshapes our very imagination of exploration. Philosophically, length contraction underscores a humbling truth. The dimensions of the world are not fixed absolutes, but mutable quantities. We often imagine the universe as an objective backdrop, a grand stage of fixed proportions. Relativity reveals instead a dynamic fabric, one that bends with motion, one that refuses to offer any observer the privilege of declaring their perspective the only true one. From a human perspective, this may feel disorienting. The idea that a spaceship, a ruler, or even the very atmosphere of Earth can be longer or shorter, depending on who observes it, challenges our trust in physical solidity. Yet it also offers a profound vision of harmony. Relativity does not reduce reality to confusion, but raises it to a deeper order, where differences in perspective are not errors, but essential features of the universe's design. And perhaps here lies the quiet existential note. If the dimensions of space itself depend on where you stand and how you move, then reality is less rigid than we imagine. There is no single map that all must follow, no universal measurement that rules them all. Instead, the universe allows for multiplicity, for perspectives that differ, yet remain true. In that sense, relativity is not only a scientific revolution, but a gentle reminder of humility, that our view of the world, no matter how carefully measured, is only one among many, and the cosmos has room for them all. Chapter 6. Relativity of Simultaneity, when now depends on you. In everyday life, simultaneity feels absolute. If two bells ring at opposite ends of a room, we assume they rang at the same moment in time, and everyone present would agree on that fact. We may disagree about which one sounded louder or came from the left or right, but the idea of when feels fixed, universal, and beyond dispute. Yet special relativity tells us that even simultaneity, one of the most basic elements of our perception of time, is not absolute. Events that appear simultaneous to one observer may not be simultaneous to another who is moving at a different velocity. The very concept of now, which we instinctively take for granted, dissolves into something relative. The seeds of this insight were planted in Einstein's recognition that the speed of light is constant for all observers. To see why this matters, imagine a thought experiment that Einstein himself described: a long train moving smoothly along a track. Lightning strikes both ends of the train at the same time, according to an observer standing at the midpoint of the track. From this perspective, the flashes of light from the two strikes travel equal distances and reach the observer simultaneously. It seems beyond dispute that the strikes occurred at the same moment. But now imagine another observer riding on the train, also sitting at its midpoint. This person is moving relative to the track observer. As the lightning strikes, the train is advancing toward the position where the front strike occurred and away from the position where the rear strike occurred. Because the speed of light is constant, the flash from the front has less distance to cover to reach the train observer, while the flash from the rear must travel farther. As a result, the passenger sees the flash from the front before the flash from the back. From their perspective, the lightning strikes were not simultaneous. The front strike happened first. Neither observer is wrong. Both are applying the same laws of physics. Both measure the same speed of light, and both interpret their observations consistently. Yet they disagree about simultaneity. The only conclusion is that simultaneity itself is not absolute but relative to the observer's frame of reference. What one observer calls at the same time, another may call separated in time. This idea is subtle because it cuts directly against human intuition. We are accustomed to treating simultaneity as universal because, at the speeds we experience, relativistic effects are too small to notice. Even when we watch distant fireworks, the differences in arrival times of light are negligible compared to our perception. But at higher velocities or across cosmic distances, the relativity of simultaneity becomes not only noticeable, but essential. The implications of this relativity run deep. It means that the universe does not offer a universal now shared by all observers. If two events occur in distant places, whether they are simultaneous depends on the frame of reference. This undermines the notion of a global present, a cosmic slice of time shared by all beings across the universe. Instead, each observer carries their own present, their own definition of simultaneity, shaped by their motion. This realization reshaped not only physics, but philosophy. In Newtonian physics, time is a single thread weaving through the cosmos, tying all events together. In relativity, time is more like a web of threads, each belonging to an observer, intersecting and diverging, without a single universal strand. The absence of an absolute now challenges us to rethink what we mean when we say something is happening at the same time elsewhere in the universe. To make this more concrete, imagine two astronomers on distant planets observing a supernova in a remote galaxy. Each records the event and measures the time it occurred according to their own local clocks. If these astronomers are in relative motion to one another, they may not agree on whether the explosion was simultaneous with some other event, like the birth of a star in a neighboring system. The disagreement is not due to error or miscalculation, but is a natural feature of relativity. The notion of simultaneity does not transcend reference frames. This concept also plays a role in the structure of spacetime as described by Minkowski geometry. In this framework, time and space are woven together, and the distinction between past, present, and future becomes more subtle. Events that are simultaneous in one frame may lie in different time orderings in another. The invariant structure of spacetime ensures consistency, but it does not preserve a universal division into now slices. The relativity of simultaneity is not a quirk or anomaly, but a fundamental property of the geometry of the universe. Einstein himself struggled with how counterintuitive this idea was, but he embraced its consequences. In his writings, he emphasized that simultaneity is not a self-evident concept, but one that requires definition through physical procedures, such as the synchronization of clocks using light signals. If two observers synchronize their clocks differently because of their relative motion, they will disagree on the simultaneity of events. This is not a defect in the method, but a revelation of the nature of time. Experimental evidence supports this aspect of relativity just as firmly as time dilation and length contraction. Particle physics provides a domain where simultaneity is tested constantly. In collisions at high speeds, the ordering of particle decays and interactions must be interpreted within specific frames. The mathematics of relativity ensures that no contradictions arise, but the results depend on the frame chosen. The relativity of simultaneity also plays a key role in resolving apparent paradoxes. In the ladder and barn thought experiment discussed earlier, whether the ladder fits entirely within the barn depends on how simultaneity is defined. For the barn observer, the entire ladder is inside at once. For the ladder observer, the front is leaving before the back has entered. Without relativity of simultaneity, these two descriptions would contradict each other. With it, they are simply two valid perspectives. The dissolution of absolute simultaneity also forces us to reconsider the flow of time itself. If now is not universal, then the division between past, present, and future is not as rigid as we imagine. Some philosophers have taken this to imply a block universe, in which all events exist equally, and the passage of time is an illusion of human perception. Others see it as evidence of a deeper relativity of reality itself, where the universe refuses to grant primacy to any single viewpoint. Physics does not settle these debates, but it provides the framework in which they must be considered. In cosmology, the relativity of simultaneity takes on grand importance. The observable universe is limited by the speed of light, and the events we see in distant galaxies occurred in the deep past. When we ask what is happening now in a galaxy billions of light years away, relativity warns us that there is no absolute answer. Depending on our frame of reference, that galaxy's present could correspond to vastly different eras of cosmic history. The very notion of a universal present moment across the cosmos becomes meaningless. This realization can be unsettling. We are deeply attached to the idea of sharing a common now with others, of existing together in the present. Relativity shows that while this may hold within our immediate environment, it does not extend across the universe. Each observer's now is unique, bound to their motion, and cannot be imposed universally. The fabric of reality is stitched together not by a single time, but by the interplay of many times, overlapping and diverging. And yet, the relativity of simultaneity does not lead to chaos or disorder. It is part of the coherent structure that preserves causality. All observers, no matter their motion, agree on which events can influence others. If one event lies in the causal past of another, all frames preserve that order. The disagreements occur only for events that are separated in such a way that no signal can pass between them. Relativity does not permit contradictions in cause and effect, only differences in perspective about simultaneity. Perhaps the most profound aspect of this idea is how it humbles our sense of time. We like to think of the present as something we share with the universe, a moment stretching from here to the most distant star. Relativity reveals instead that the present is local, personal, and relative. What we call now is not a cosmic truth, but an observer-dependent slice of space-time. And here lies the quiet existential reflection. If now is not universal, then perhaps our attachment to the present moment is also less absolute than we imagine. Each of us carries a personal now, stitched into the vast fabric of space-time, overlapping with some, diverging from others, never extending infinitely. The universe does not give us a single present to share, but countless presents, each valid in its own frame. In this, we glimpse a universe that is at once less comforting and more wondrous, a cosmos where time itself resists simplification, inviting us to accept its multiplicity. Chapter 7. E equals mc squared, the energy-mass connection. Few ideas in the history of science are as widely recognized and yet as profoundly misunderstood as Einstein's relation that energy equals mass multiplied by the speed of light squared. It appears simple, consisting of only a few symbols, yet it encapsulates a transformation in how we understand the universe. It tells us that mass is not an immutable property of matter, but a condensed form of energy, and that energy itself is bound to the very fabric of matter. When Einstein first derived this relation in 1905, it was not presented as a headline or a grand revelation. It appeared almost quietly near the end of one of his papers on relativity. Yet its consequences would ripple outward through physics, reshaping our understanding of atoms, stars, and the cosmos itself. To understand why this relation arises, we must recall the central feature of relativity, the constancy of the speed of light and the invariance of the laws of physics for all observers moving at steady velocity. These principles force a rethinking of how quantities like momentum and energy behave at high speeds. In Newton's world, Momentum was simply mass times velocity, and energy was 1/2 of mass times velocity squared. But as velocities approach the speed of light, those formulas no longer suffice. To preserve consistency across frames, new relationships are required, and from them emerges the realization that mass itself contributes to energy, independent of motion. Even an object at rest carries energy by virtue of its mass alone. This so-called rest energy is given by Einstein's relation. It tells us that even a small amount of matter contains an extraordinary reservoir of energy. To put this in perspective, if the mass of something as small as a paperclip could be completely converted into energy, the release would equal that of a large nuclear explosion. The everyday solidity of matter hides an unimaginable store of energy bound within it. The recognition of mass-energy equivalence transformed physics into a more unified science. It showed that energy and matter are not separate categories, but two forms of the same underlying quantity. Mass can be transformed into energy, and energy into mass. This realization is not only theoretical, but observable. When particles collide at high energies, new particles with mass can be created. In nuclear reactions, small differences in mass appear as large releases of energy. The sun itself shines because of this principle, converting mass into light and heat through nuclear fusion in its core. In nuclear physics, this explains why the energy released in nuclear reactions is so vast compared to ordinary chemical processes. In combustion, say, burning coal or wood, energy comes from rearrangements of electrons around atoms. The masses of the nuclei remain unchanged, but in nuclear fission and fusion, changes occur in the very structure of the nuclei, and the difference in binding energy translates directly into released energy. Even a tiny fraction of mass loss corresponds to enormous energy, because the speed of light squared is such a large factor. This principle underpins both the destructive power of nuclear weapons and the sustaining light of the stars. In the sun, hydrogen nuclei fuse to form helium, and the resulting helium atom has slightly less mass than the original hydrogen nuclei. That missing mass is not lost, but converted into energy, which radiates outward as sunlight. Over billions of years, this process gradually reduces the sun's total mass, though by amounts negligible on human timescales. Without this conversion of mass into energy, life on Earth would not exist. Particle physics has revealed even more striking confirmations of mass-energy equivalence. In accelerators, when particles are smashed together at extreme velocities, new particles can appear that are more massive than the originals. The extra mass comes from the energy of motion. Conversely, unstable massive particles decay into lighter ones, plus bursts of radiation, conserving the total energy mass of the system. The universe continually demonstrates this interchangeability. The relation also reshaped our understanding of conservation laws. In classical physics, mass and energy were considered separate conserved quantities. Relativity merged them into a single conservation law. The total mass energy of a closed system remains constant. This principle underlies everything from the stability of stars to the balance of reactions in laboratories. It is important, however, to clarify what energy equals mass times the speed of light squared does and does not mean. It does not suggest that mass can casually disappear into energy in everyday processes. The conversion requires conditions where nuclear or particle interactions occur. A rock sitting on the ground does not spontaneously radiate away its mass as energy. Instead, the relation tells us that the rock's very existence as matter carries with it an enormous quantity of stored energy, whether or not it is released. The power of this insight lies not only in its applications, but in the way it unifies our picture of reality. Before Einstein, matter and energy seemed like fundamentally different entities. Matter was substance, solid and enduring. Energy was activity, motion, or heat. This relation revealed them to be manifestations of the same underlying reality, different guises of a single essence. In astrophysics, this equivalence explains phenomena on the grandest scales. The luminosity of stars, the dynamics of supernovae, and the synthesis of heavy elements all depend on the conversion of mass into energy. When a massive star ends its life in a supernova explosion, the sudden release of energy comes from the rearrangement and fusion of nuclei, with mass-energy equivalence dictating the scale of the event. The elements that make up planets and living beings are forged in such processes, scattering the products of mass-to-energy conversion across the galaxy. The relation also enters cosmology, where the balance of mass and energy in the universe shapes its evolution. Even massless particles like photons carry energy and contribute to the overall energy density of the cosmos. The universe's expansion, its thermal history, and the cosmic microwave background are all described in terms of mass-energy content. Relativity ensures that matter and radiation are different aspects of the same story. Technologically, the mastery of mass-energy conversion has changed human history. Nuclear reactors harness controlled fission to release energy that powers cities. Medical technologies such as positron emission tomography rely on the annihilation of particles and antiparticles, converting their mass into detectable radiation. At the frontier of research, particle colliders continue to probe the transformations of energy into mass, recreating conditions that resemble the earliest moments after the Big Bang. Despite its fame, the equation remains easily misrepresented. Popular accounts sometimes suggest it explains why nuclear bombs explode or why stars shine, as though the relation itself is the mechanism. In reality, it is the principle that enables us to calculate the energy yield of processes that convert mass differences into radiation or kinetic energy. It is a statement of equivalence, not a recipe. Its power lies in its universality. One might also ask, why does the speed of light squared appear in this relation? The answer lies in the geometry of space-time itself. The factor arises naturally from the relativistic relationships between energy, momentum, and mass. The speed of light serves as the conversion constant between units of mass and energy, linking them in a way that reflects the underlying structure of physical law. It is not arbitrary, but a reflection of how the universe itself is woven together. There is also a subtlety in how physicists interpret the terms. Mass in this context refers to rest mass, the intrinsic property of an object independent of motion. Energy includes both rest energy and kinetic energy. The relation does not mean that moving objects gain mass in the everyday sense, but that their total energy increases. This distinction matters in modern physics, where precision is essential, but the essential insight remains. Mass and energy are interchangeable, bound by a constant of nature. From a broader perspective, the mass-energy connection underscores a theme in physics, that simplicity can conceal profound depth. Three elements, energy, mass, and the speed of light, capture an idea that reshapes how we see stars, atoms, and ourselves. The clarity of the expression belies the richness of its meaning. And perhaps here we can pause for a quiet reflection. If matter is condensed energy, then everything around us, the chair you sit on, the air you breathe, your own body, is a form of frozen light, bound into substance by the rules of physics. The energy that blazes in the cores of stars is the same energy bound in every atom of your being. The universe reveals itself not as a collection of separate categories, but as a continuous transformation of one essence into another. And maybe there is something humbling in realizing that the solidity of matter is not so solid after all, but a temporary arrangement of energy destined to transform, to radiate, to return to the wider cosmos. In this sense, energy equals mass times the speed of light. Squared is not only a scientific relation, but a quiet reminder that even the most enduring things are part of a ceaseless exchange. Energy and mass flowing into one another, shaping the story of the universe across time. Chapter 8. Paradoxes that aren't. Twin paradox and beyond. One of the surest signs that a scientific theory has touched something deep about reality is that it generates apparent paradoxes. These are scenarios that, when described in ordinary language or thought experiments, seem contradictory, even absurd. Special relativity, with its insistence that time and space depend on the observer, has produced many such puzzles. They are often called paradoxes because they challenge intuition, but none of them, once carefully examined, truly undermines the theory. They are not paradoxes in the sense of irreconcilable contradictions. Rather, they are invitations to rethink our assumptions and to glimpse the strange but consistent structure of space-time. Perhaps the most famous of these is the so-called twin paradox. It is a story simple enough to capture the imagination, yet profound enough to trouble even those who study relativity seriously. Imagine two identical twins. One stays on Earth while the other boards a spacecraft and travels close to the speed of light before returning home. According to relativity, time for the traveling twin flows more slowly compared to the twin who remains on Earth. When they reunite, the traveler has aged less. In some versions, the difference is only a few years. In others, depending on the speed and duration of the journey, it could be centuries. At first, this seems straightforward, until one recalls the principle of relativity itself. If all motion is relative, could we not equally well say that the twin on Earth was the one moving while the spacecraft remained at rest? In that case, wouldn't the Earth-bound twin be the younger one when they meet again? Each twin could point to the other as the traveler, and so the situation seems symmetrical. How then can relativity produce an unambiguous result? The resolution lies in the details of the journey. The twin who departs Earth must accelerate to reach high speed, decelerate to turn around, and then accelerate and decelerate again to return. These periods of acceleration break the symmetry. The twin on Earth remains in a single inertial frame while the traveler switches between frames. Special relativity applies cleanly only to inertial motion, but when acceleration is taken into account, the mathematics yields a consistent answer. The traveling twin is younger. This is not a flaw in relativity, but a consequence of applying it carefully. Experiments, though not with human twins, have confirmed the effect. Fast-moving particles decay more slowly than identical particles at rest, just as the traveling twin's body would age more slowly than the one left behind. Atomic clocks flown on aircraft or satellites record measurable differences in elapsed time compared to clocks on the ground, matching the predictions. The twin paradox is not just a thought experiment, but a reflection of the universe's behavior. Philosophers and physicists alike have reflected on the deeper implications of this scenario. It is not just about comparing two clocks, but about comparing two lives. The paradox dramatizes the idea that time itself is personal, linked to one's path through space-time. Two people born together can diverge not only in experience, but in the very number of years they live before reuniting. The story of the twins captures the essence of relativity, that time is not universal, but relative to motion. Beyond the twin paradox, other scenarios often spark confusion. One is the ladder paradox, sometimes called the barn paradox. In it, a long ladder is carried at relativistic speed into a barn shorter than the ladder's rest length. From the barn's perspective, the ladder contracts and fits neatly inside, even allowing the doors to close momentarily. From the ladder's perspective, however, it is the barn that contracts, making it impossible for the ladder ever to be fully enclosed. At first glance, this seems contradictory, but the resolution comes from the relativity of simultaneity. For the barn observer, there is a moment when the entire ladder is inside. For the ladder observer, the front has already emerged before the back has entered. Each description is valid in its own frame, and no contradiction arises once simultaneity is recognized as relative. Variations of this paradox add richness. What if the doors are closed simultaneously in the barn's frame? Then indeed the ladder fits. But in the ladder's frame, the rear door closes after the front door opens. The doors never trap the ladder, and again, no contradiction arises. The paradox highlights how our intuition about simultaneity fails when objects move near the speed of light. Another well-known puzzle is the Ehrenfest paradox, which concerns a rotating disk. In relativity, objects moving at high speed contract in the direction of motion. If a disk spins rapidly, the circumference moves at high speed relative to the center, and thus should contract. But the radius perpendicular to the motion does not contract. If the radius remains the same while the circumference shrinks, the familiar relation between circumference and radius from Euclidean geometry no longer holds. This appears paradoxical, but in fact reveals an important truth. In relativity, space is not strictly Euclidean. The geometry of a rotating disk is curved. What the paradox uncovers is not a contradiction, but a glimpse of non-Euclidean geometry, which later became central to Einstein's general relativity. There is also Bell's spaceship paradox, another scenario designed to test the edges of relativity. Imagine two spaceships connected by a thin thread, both accelerating in unison as seen from an external observer. Will the thread break? Intuition might suggest not, since both ships move together. But relativity shows that because of length contraction and the relativity of simultaneity, the distance between the ships as measured in their own accelerating frame actually increases. The thread is stretched and eventually breaks. The paradox dissolves once the proper relativistic description of acceleration is applied. Other paradoxes play with similar themes. In the so-called pole in the barn version of the ladder paradox, a runner carries a pole that is longer than a barn but fits inside because of length contraction. In some retellings, the runner insists the barn is contracted so the pole cannot possibly fit. Once again, the key lies in simultaneity. In the barn's frame, the entire pole is inside at one instant, while in the runner's frame, it never is. There is no contradiction, only differing perspectives. Another classic is the watch and spaceship paradox, in which observers argue about whether two clocks remain synchronized after one undergoes acceleration. Confusion arises because people attempt to apply inertial logic to non-inertial frames. Once acceleration and relativity of simultaneity are properly accounted for, the predictions agree perfectly. What unites all these examples is that they arise from trying to apply Newtonian intuition to relativistic situations. Our everyday experience teaches us that lengths are fixed, time is universal, and simultaneity is absolute. When those assumptions fail at high speeds, paradoxes seem to emerge. But when the full machinery of relativity is applied, they are resolved and consistency is restored. Relativity does not invite contradiction. It demands a more subtle logic. The persistence of these paradoxes in popular imagination speaks to how deeply counterintuitive relativity remains. Even more than a century after Einstein's work, the idea that time and space can change depending on motion still feels foreign. It is easy to imagine a spaceship moving near light speed. It is harder to accept that such motion alters the fundamental measures of length and simultaneity. The paradoxes give us a way to confront that discomfort, to wrestle with the consequences until they become, if not intuitive, at least coherent. It is also important to emphasize that relativity preserves causality. None of these paradoxes allow an effect to precede its cause or create genuine contradictions in physical law. The apparent contradictions come from mixing frames of reference without accounting for how relativity transforms between them. Once those transformations are included, the puzzles vanish. The universe remains orderly, even if its order is stranger than we once imagined. On a deeper level, the so-called paradoxes highlight the relativity of human perspective. We tend to assume that our view of the world, our sense of simultaneity, our definitions of length and time, is the natural one. Relativity reveals that such assumptions are bound to our limited range of speeds and scales. In the broader universe, perspectives differ, and all are valid within their own frames. The twin paradox, in particular, invites existential reflection. It reminds us that time itself is not a universal rhythm, but a personal one, linked to one's path through space-time. Two lives beginning together can diverge not only in experience but in the very number of years they live before reuniting. The notion that a traveler could return to find decades passed while only years slip by for them is not only possible but inevitable under relativity. And perhaps this is the quiet lesson behind all the paradoxes, that reality resists being reduced to a single narrative. The universe does not grant one privileged frame of reference or one absolute now. It offers a web of perspectives, consistent but relative, each revealing its own truth. What seems paradoxical at first is simply the mismatch between our intuition and the cosmos's deeper order. As you drift towards sleep, consider that these paradoxes are not failures of logic, but invitations to expand it. They show us that the universe is more subtle than our instincts suggest, but also more coherent. The cosmos allows no contradictions, only new ways of seeing. And in that recognition lies both humility and wonder, that even in its strangest puzzles, reality remains whole, consistent, and beautifully resistant to simplicity. Chapter 9. Experiments that prove special relativity. The true strength of a scientific theory lies not in its elegance or its ability to capture imagination, but in its ability to withstand the scrutiny of experiment. Einstein's special relativity, proposed in 1905, emerged from a combination of logical reasoning, mathematical consistency, and insights into the constancy of light. Yet for all its boldness, it would have remained speculation if not for a century of empirical confirmations. The beauty of relativity is not only that it transforms our understanding of time, but that it has been tested, refined, and confirmed in countless experiments. Each test, whether performed with light beams, atomic clocks, or high-energy particles, has reaffirmed the same truth. The universe behaves exactly as relativity predicts. The earliest experimental hints came even before Einstein's work. The most famous of these is the Michelson-Morley experiment of 1887, an attempt to detect the motion of Earth through the hypothetical luminiferous ether. If light were a wave, physicists reasoned, it must have a medium in which to propagate, just as sound requires air or water requires the sea. By splitting a beam of light and sending the parts along different paths, Michelson and Morley expected to measure a difference in their travel times depending on the Earth's velocity through this ether. But no such difference was observed. The speed of light appeared constant in all directions, regardless of Earth's motion. The result was baffling at the time, but it later became one of the cornerstones supporting Einstein's postulate that the speed of light is invariant for all observers. A few years later, further optical experiments reinforced this conclusion. Variations of Michelson-Morley with greater sensitivity, as well as experiments involving moving sources of light, consistently failed to detect any motion through an ether. These null results did not immediately overturn classical physics, but they created mounting tension. The absence of an ether wind demanded explanation, and relativity eventually provided it. No ether was needed because the speed of light is constant in all inertial frames. After Einstein proposed special relativity, experimentalists sought more direct confirmations of its predictions. Among the first was the observation of time dilation in radioactive particles. Unstable particles such as muons, created when cosmic rays strike the upper atmosphere, decay rapidly, with lifetimes far too short to allow them to reach Earth's surface at ordinary speeds. Yet detectors on the ground consistently record their arrival in large numbers. The explanation is relativity. From our perspective on Earth, the muons' internal clocks tick more slowly because they are traveling close to the speed of light. They live longer, long enough to penetrate deep into the atmosphere and reach detectors. From the muons' own perspective, their lifetimes are unchanged, but the atmosphere they must traverse is contracted, allowing them to cover the distance. In either frame, the predictions of relativity resolve the puzzle, and the experimental data match perfectly. Controlled laboratory experiments have replicated this phenomenon with precision. Particle accelerators routinely create unstable particles moving at relativistic speeds, and their decay times are measured with exquisite accuracy. Each time, the observed lifetimes are extended exactly as relativity predicts. The muon, once a curiosity from cosmic rays, has become one of the best confirmations of time dilation in the laboratory. Another striking test came from experiments with fast-moving atomic clocks. In 1971, Joseph Hafeel and Richard Keating placed 4 cesium beam atomic clocks aboard commercial airliners that circled the globe, some eastward, some westward. When the clocks were compared to those kept stationary at the U.S. Naval Observatory, they showed measurable differences. The airborne clocks had experienced time differently depending on their direction of travel, their speed, and their altitude. The results were in precise agreement with relativity, which had predicted not only time dilation from velocity, but also gravitational effects described by general relativity. This experiment, performed with technology available half a century ago, confirmed in real-world conditions what Einstein had described in abstract theory. Modern technology relies on these relativistic effects to function. The Global Positioning System, a network of satellites orbiting Earth, depends on clocks accurate to billionths of a second. Yet these clocks tick differently from those on the ground because of both their speed and their position in Earth's gravitational field. Engineers must correct for these relativistic effects, or GPS positions would drift by kilometers each day. The fact that your phone can tell you your location with astonishing accuracy is possible only because relativity is true. Experiments with high-energy physics have further confirmed length contraction and energy mass equivalence. In accelerators like the Large Hadron Collider, particles are accelerated to speeds within a fraction of a percent of the speed of light. Their behavior under collisions, their production of new particles, and their decay patterns all match the predictions of relativity. For example, the equivalence of mass and energy is demonstrated every time a high-energy collision creates particles heavier than those that entered. The additional mass comes from the kinetic energy of the collision, transformed exactly as relativity demands. Other precision experiments have tested the relativity of simultaneity and the invariance of light's speed. One approach involves comparing atomic clocks separated by large distances and linked through networks of lasers. These comparisons show that no matter the orientation of the system or the Earth's motion through space, the speed of light remains invariant. Similarly, particle physics experiments with electron-positron collisions have demonstrated that the rules of relativity hold even under extreme conditions of energy and velocity. In the 20th and 21st centuries, technology has reached levels where relativity can be tested with breathtaking accuracy. Optical lattice clocks, among the most precise devices ever built, can measure differences in time dilation when one clock is raised by just a few centimeters in Earth's gravitational field or moved at tiny velocities. Even such minuscule effects align with relativity's predictions. The theory has survived every attempt to find deviations. There are also astrophysical confirmations. When jets of plasma shoot from the centers of active galaxies, they move at speeds so close to light that their behavior must be interpreted using relativistic models. The observed radiation and apparent motions confirm time dilation, relativistic beaming, and other effects predicted by Einstein. Likewise, the observation of high-energy cosmic rays, which travel across millions of light years, matches expectations only if time dilation extends their lifetimes in transit. Even the discovery of gravitational waves in 2015 indirectly confirmed the consistency of relativity at high precision. Although gravitational waves belong to general relativity, their propagation at the speed of light and their detection through interferometry reaffirmed the invariance of light speed that underpins special relativity. It is worth pausing to recognize that these experiments span scales from the subatomic to the cosmic. They involve delicate laboratory clocks, massive particle colliders, satellites orbiting Earth, and signals from galaxies billions of light years away. Yet all of them tell the same story. Relativity's predictions hold. No matter how strange its claims about time, space, and simultaneity may seem, the empirical world continues to validate them. This unbroken record of confirmation has a philosophical weight. It shows that relativity is not merely a clever reinterpretation of mathematics, but a faithful description of reality itself. The constancy of light speed, time dilation, length contraction, the equivalence of mass and energy, all are not only ideas in textbooks, but physical truths etched into the behavior of particles, the ticking of clocks, and the light of distant stars. And perhaps there is something existential in this. The experiments remind us that our intuitions, shaped by slow movements and short lifetimes, are not reliable guides to the universe. Reality is deeper, stranger, and more coherent than common sense would allow. That a plane flying around the world or a particle racing through a collider can alter its experience of time shows us that even the most familiar quantities are relative. In these experiments, we glimpse a universe that does not conform to our expectations, but to its own profound order. As you rest, you might think of those tiny muons streaking through the atmosphere, their lives stretched by their speed, or of atomic clocks circling the globe, each ticking at its own rhythm. These experiments are not just tests of a theory. They are reminders that time and space are malleable, woven into a fabric far subtler than our senses reveal. The cosmos, tested and measured again and again, whispers the same truth. Relativity is real, and in its strange order lies a beauty beyond intuition. Chapter 10. How Special Relativity Changed Our Universe. When Albert Einstein submitted his 1905 paper on the electrodynamics of moving bodies, he likely did not imagine that he was altering the course of human thought as profoundly as Copernicus or Newton had centuries before. At the time, it was one of several works he produced in what has since been called his miracle year. Yet among those papers, Special Relativity was the one that permanently shifted the foundations of physics. What began as a re-examination of how light behaves soon reshaped our understanding of time, space, energy, and motion. Its consequences ripple outward into modern technology, cosmology, and even philosophy. The immediate impact of special relativity was to break the centuries-old idea of absolute space and time. Newton had envisioned a universe in which time flowed uniformly everywhere, a cosmic clock ticking in unison across the stars, and space provided a rigid, immutable stage on which events played out. This view was not merely scientific, but almost metaphysical. It gave people confidence in a universe ordered by absolutes. Einstein dismantled that certainty. In its place, he offered a universe woven together by relative measures of time and distance, bound by the constancy of the speed of light. It was not that the cosmos had lost its order, but that its order was subtler, more relational, and more deeply intertwined than previously imagined. The philosophical shock was immense. Suddenly, questions that had seemed straightforward, such as whether two events happened at the same time, had no universal answer. Simultaneity became relative, time became personal, and distances depended on perspective. These were not abstract musings, but direct consequences of experimental fact. The Michelson-Morley experiment had already hinted at the collapse of the ether concept. Einstein completed the revolution by declaring that no ether was needed. The universe itself had no preferred frame, no ultimate perspective. Reality was egalitarian, granting validity to every inertial observer. This restructuring of time and space was not accepted overnight. Many physicists initially resisted, some preferring alternative explanations, such as Lorentz's ether theory. The idea that time itself could flow differently for different observers seemed too radical. Yet within a few years, the mathematical consistency of relativity and its agreement with experiment won converts. Max Planck, already famous for founding quantum theory, was among the first to recognize the theory's significance. Hermann Minkowski soon reformulated it into the geometry of four-dimensional spacetime, giving the theory an elegant mathematical framework that deepened its reach. By the 1920s, relativity had become foundational to physics, taught in universities and applied to new problems. What had seemed outrageous in 1905 was, within 2 decades, indispensable. The philosophical impact extended far beyond physics. Writers and thinkers seized on relativity as a metaphor for a world in which absolutes were dissolving. In art and literature, movements such as Cubism and Modernism played with fractured perspectives and multiple viewpoints, echoing the relativity of simultaneity. philosophers debated whether relativity implied a deterministic block universe, in which past, present, and future coexist equally. Others wondered whether it undermined human freedom or reinforced it by showing the diversity of perspectives. Relativity became more than a scientific theory. It became a symbol of modernity itself, embodying the collapse of old certainties and the embrace of new, unsettling truths. Special relativity also redefined the concept of energy. The realization that mass is a form of energy changed not only physics but technology. Nuclear energy, whether in reactors that light cities or in weapons that destroy them, is a direct consequence of Einstein's insight. The equivalence of mass and energy explained why the sun shines, why stars live and die, and why the cosmos itself evolves. It bound together the smallest scales of particle physics with the largest scales of astrophysics. The theory revolutionized experimental practice as well. Particle accelerators, designed in the 20th century and still central to physics today, operate entirely within a relativistic framework. They accelerate protons and electrons to speeds close to that of light, requiring relativistic equations to describe their behavior. Without relativity, such machines could not be designed or interpreted. Every discovery made in high-energy physics, from quarks to the Higgs boson, rests on the scaffolding of Einstein's 1905 insight. Technology in daily life, too, is shaped by relativity. Global navigation systems, which depend on atomic clocks aboard satellites, must correct for time dilation due to both their speed and their position in Earth's gravitational field. The engineers who designed them did not include relativity out of philosophical preference, but because without it the system would fail. Each time a smartphone locates its user with meter-scale precision, it demonstrates that relativity is not merely an abstract theory, but an active component of modern infrastructure. Medical technology, though less obvious, also benefits from relativity. Positron emission tomography, PET scanning, relies on the annihilation of particles and antiparticles, in which their mass is converted into photons of pure energy. This principle derives directly from mass-energy equivalence. The ability to peer into the human body with such precision, to diagnose disease at early stages, is a consequence of Einstein's insight into the deep connection between mass and energy. Relativity also changed the way humanity conceives of travel and exploration. Though we have yet to build spacecraft capable of approaching light speed, the thought experiments of relativity shape our imagination of interstellar journeys. The twin paradox reminds us that high-speed travel comes with the price of time dilation. Travelers may return home to find centuries past. This reality reshapes how we dream about colonizing the stars, grounding those dreams in the unyielding limits of physics. For science fiction writers, relativity became a narrative boundary, sometimes respected, sometimes circumvented with imagined technologies like warp drives or wormholes. But even those fictions acknowledge Einstein by defining themselves in relation to his limits. Cosmology, too, owes much to special relativity. The framework of space-time, the interplay between energy and mass, and the constancy of light speed all form the foundation upon which general relativity was built. General relativity then gave rise to modern cosmology. The expanding universe, the Big Bang, black holes, and gravitational waves. Without special relativity, there could be no general relativity. Without general relativity, our view of the universe's origin, structure, and fate would remain incomplete. What makes the impact of special relativity remarkable is not only its reach, but its resilience. For more than a century, physicists have tested its predictions with ever greater precision. Atomic clocks, subatomic particles, and astrophysical phenomena all behave exactly as relativity demands. No experiment has yet contradicted it. This robustness is a hallmark of great science. Ideas that begin as radical challenges to intuition become pillars of knowledge, shaping every generation that follows. And yet, for all its success, special relativity also left open questions. It reconciled mechanics with electromagnetism, but did not incorporate gravity. It reshaped our view of space and time, but did not address the quantum behavior of matter. Einstein himself, after publishing his general theory in 1915, spent much of his later career searching for a deeper unification, one that might bring relativity and quantum mechanics together. That search continues today, with string theory, loop quantum gravity, and other approaches, all seeking to extend the legacy of relativity into a broader framework. The cultural legacy of relativity endures as well. It symbolizes the modern scientific spirit, bold enough to question the most basic assumptions, rigorous enough to follow reason wherever it leads, and humble enough to accept that reality may be stranger than intuition. It has entered language itself. To say something is relative is to acknowledge the lesson Einstein made famous, that truth may depend on perspective. There is, too, an existential echo in its lessons, to learn that time is not absolute, that simultaneity is not universal, and that mass is simply another form of energy, is to confront a universe stranger than intuition allows. We are reminded that our everyday sense of reality, shaped by slow speeds and small scales, is not the measure of truth. The cosmos moves according to deeper laws, indifferent to our assumptions. And perhaps that is the quiet gift of special relativity. It tells us that reality is consistent, but not simple, coherent, but not comforting in the ways we once imagined. It reveals a universe without a single center, without an absolute present, without a privileged perspective. Yet in stripping away those absolutes, it gives us something richer, a vision of the cosmos as a web of relationships, where every observer carries their own time, their own space, and yet all are bound together by the same laws. As you rest, you might think of how extraordinary it is that such a profound shift came not from vast observatories or grand experiments, but from the imagination of a young man working in a patent office. With clarity and courage, Einstein asked what would happen if one took the speed of light seriously, if one followed its consequences without compromise. Out of that question came a theory that reshaped not only physics, but our conception of reality itself. The universe we inhabit is no longer Newton's fixed stage, but Einstein's dynamic, relative space-time. And in that realization lies a humbling beauty, that the cosmos is far stranger and far more wondrous than the world of absolutes we once believed in. And so, my friend, we come to the end of this quiet journey through special relativity. If you're still awake, I invite you to explore another video waiting for you just beyond this one, filled with more gentle science to dream to. But if your eyelids are already heavy, then let go, rest deeply, and let the universe keep watch. Sweet dreams among the stars.